Log on, tune in, find out. Another good idea from Cambridge.
Today we're going to have two talks, and the first talk is by Giuseppe Primiero from Gent University, and he's going to tell us about practical reasoning with proofs and types.
Thank you. Thanks everyone. So I thought it would be nice to start this presentation with a reference of something I've been rereading recently. This will be basically the motivation of this talk, and then I will go through part 2 and 3, which are the things that I've more or less already done, and I will tell you about this, and then part 4 is basically what I aim to do in the next 4 weeks for the first period I will be here, and I will conclude with a short summary of the whole talk. So what is the motivation and what is the reference I was talking about? This is a reference to Turing. In 1948 he wrote this, the paper was published in 1948, probably written around 1946. The paper was titled Practical Forms of Type Theory, and this is more or less a quote from the paper. A theory of type with small use of type themselves in a way that reflects the practice of proving by mathematicians. It's quite interesting, both historically, because it was written probably during the period it was back in the US, and at the same time it was working on the analytic computing engine. So there are a number of things that goes around, but the most important thing to me was that there are a number of things that actually come out as interesting also in view of the later development of type theory, in particular for the intuitionistic foundation. So this is more or less what the highlight that I consider important to the work you will see later. So this type system is construed from below. It starts from individuals, objects of type 0, and then it constructs functions on top of that as objects of type 1, taking arguments from type 0 to arguments of type 0, and so on. So this is clearly something that, looking at the intuitionistic foundation, is at least reminiscent of what will happen later. But there are two important things that happens here. One is that it introduces an individual as the value of undefined functions. It calls this C, and this is of course to prevent bad typing. And then introduces interpretability under hypothesis. Also in this case, you see the derivability relation under hypothesis is strongly embedded into the intuitionistic reading of type theory. So these are a little bit of things that looks at the stay at the background of what I'm doing now, and this gives a little bit of the justification for why I titled this talk practical reasoning. So what do we mean by practical reasoning? I'm looking at forms of reasoning with hypothetical judgments is one thing. I'm looking at distinction between partially and fully evaluated expression in the systems in order to keep them as much as possible apart from one another. And I working on application of this distinction in natural deduction reasoning, in particular using the distinction between valid and true assumptions, or global and local assumptions. So this is what I actually mean by practical reasoning, reasoning by types that, by type system that satisfy these ideas. And then what we mean by proofs and types, I'm looking at extensions of the probability and realizability models intended by the Brouwer-Eyting-Kolmogorov semantics. Up to now I've working on two things. One are dependent types with modalities to express both partial termination and distributed computing. I'm not going to talk about this, but this might be interesting to someone maybe. The one thing I will talking about today, which is the work I will be doing, finishing here at the Newton Institute, is an extension of the logic of proofs with the notion of dependent justification. So this is what I will talk in the next 15 minutes maybe. So what is intuitionistic logic of proof with dependency relation? First, a little bit of background. Logic of proofs provides an explicit reading of modal logic S4 with the probability semantic for the propositional, in the case of now, in the specific case, intuitionistic propositional logic. In this system, knowledge and belief modalities are decrypted in the form of proof terms or justification terms. And what are justifications? Justifications are For example, in the case of a mathematical language, these are formal proofs and are considered as abstract objects which have structure and have operation that are applied on them. The basic operations are usually application to construct implication and sum to construct composition of proofs. In the minimal setting I will talk about, we are looking only at application and proof checking. I will explain what these things are. So what is the standard? So for now, just the standard setting of intuitionistic logic of proofs is a language that contains a countable set of symbols for propositions, individual variables in brackets for proof terms and the related constant to substitute those proof terms, those proof variables, and then it has predicative expression and functional symbols. The two functional symbols I will use are, as I said, application and the proof checker. The proof checker is basically the operation that iterates proof, and it simulates the axiom for iteration of boxes from S4. These are again the axioms for the standard language. It contains the axiom schemes of minimal logic in the language, translated in the language of the logic of proofs, and then it has well, unconditional evidence or simply evidence, proof checker for iteration of proof terms, application for implication, and then two rules, modus ponens and necessitation, to provide the proof constants of each of the axioms above. So this is the standard setting of the language. What I want to do is basically to extend this language in a way that allows to introduce dependent proof terms. So the notion of proof terms, dependent proof term that I'm looking about is inspired from the corresponding notion that it is known from theories of dependent types. And just a reminder, what is a dependent type? A dependent type is a type expression of the form b of x, where x is a free variables that is typed in another type, so that one can say that b is a type whenever x is in type A. In this way, one can construct propositional functions, given that there is the analogy between proofs and types, and standardly this is used to compose the sigma and the pi type for the corresponding quantifiers. Okay, so this is what a dependent type is. What do we want to do is to give a notion of dependent proof term in the setting of intuitionistic logic of proofs, to build an expression of this form. T is a proof term for B whenever A is a proof term, whenever A has a proof term S. Now, an important point will be to understand what do we mean by A as a proof term for S, and my interest lies in giving two different readings of this. The two different readings will be basically when A is actually justified, so S is an actual proof term for A, and when A is possibly justified or just assumed to be true. And this is the case when one assumes there is such a proof term S, though the proof term is not yet constructed. So these are the two reading of the dependent term that I'm looking at. And the aim is to translate these to a derivability relation in natural deduction calculus and to prove some meta-theoretical results, namely equality rule, substitution lemma, contractions and expansions on connectives, and finally normalization for the system. As I mentioned already, normalization is a bit the tricky part that I'm looking right now at. So what is the, how do we extend now the language? The idea is that we keep, of course, the first reading of the standard formula. So we denote the fact that S is the proof term of proposition A, but the formula box S A. And then we add a new formula, which is angle bracket S bracket T B A. This is this expresses the fact that T is a proof term of proposition B whenever S is the proof term for proposition A, and we extend the proof terms accordingly. So we'll have composition, we will have proof checking, we will have composition of separate proof terms. I will explain what is this, and an abstraction on proof terms. The good thing is that once this extension is done, one can do something which is pretty similar to what happens to types under context. Namely, in context, one usually adds multiple dependency relations. So one is able to express the fact that a certain type is dependent from a set of types A1 to AN, where all the types are dependent from one another. We can do the same in this setting. So we can extend actually to multiple dependent terms, and we can use this to add quantification over proof terms. So we will get also expression of this form. This is, once this object is introduced, this extension is pretty natural, whereas in the standard case of the logic of proofs, the extension to quantification of formula is a bit ad hoc, and it requires a much stronger apparatus. That should be not axioms but rules. So in order to work with this object, we need to add also two additional rules. So the first rule is the rules for dependent evidence. What this rule says is that if A is a proven object and B can be derived, proof object T for B can be derived under A, then one can construct the dependent evidence for B depending on A. And one can discharge this by application of dependent evidence. So this is the additional rules to the system. Now, what is interesting is that this can be translated into a natural deduction calculus, but it's not a standard natural deduction calculus. I will try to explain how this is the case. So the translation to natural deduction calculus happens by distinguishing global from local assumptions. Usually this is not something that is done in the natural deduction calculi, but the idea is the following. One will have an expression for unconditional evidence. This is the one above, and you see the the formula is slightly changed in order to describe the difference, but you can read A bar S as S is a proof is an evidence for A, and an unconditional evidence holds if the assumption on the left hand side of the sequent are all valid assumptions. So here you see this is just delta. The case of a dependent evidence, which is indicated by the double bar, is given when the derivation is allowed from sequence that contains not only valid assumptions but also at least one true assumption, so one assumption that is not already discharged. And this will be the two basic formula of the natural deduction calculus. What does the language look like? Well, the language looks like a set of proof terms which preserves the standard variable for proof term application, proof checking, and the elimination of the proof checking. This is the extract operation, plus two other proof term, namely the question mark proof term, which is the one infers from the dependent evidence, and the discharging for it. So the assumption operation is the elimination rule. Therefore, I will show the rule in a second. Also, the propositions are extended. So there is variable for proposition, there is application, and then there is the B bracket A is the corresponding function formation rule. So it will result from a function formation rule or a dependent evidence formation rule. And well, the bracket SA is the standard operation in the language. We add the angle bracket SA and the dependent evidence rule. Contexts are divided into truth context for context that contains true assumptions, and validity context for contexts that contain valid assumption. Now, what are the derivation rules for the system? The system contains two starting rules, so the validity variable and the true variable. These are respectively the rules that allow us to use a proof term from a validity variable and a proof term for a true assumption. And you will see that the implication relation is built up by only valid assumption and function formation. Well, this can be read as dependent evidence formation rule. The dependent evidence formation rule is built up by derivation from true assumptions. So basically the system is split in two parts. It looks at one way for derivation that contains only discharged assumptions, and it looks with another derivability relation for operations derivable from true assumptions. When this is done, one can of course use operators to internalize this distinction, and the operators are of course model operators. So we will have respectively introduction and elimination rule for the box operator, which is inferred from unconditional evidences, and the diamond operator, which will be instead inferred from dependent evidence. So this is of course this rule are proven to be to have appropriate contraction and expansion rules. In particular, these are all properties that can be shown to hold for the system, namely structural properties. There is only a restricted version for exchange, because when you look at exchange in the set of true assumptions, you cannot simply mix up the order there. So you will have a restricted form of exchange that holds only for valid assumptions, where the rest of the structural properties are entirely fine for both unconditional and dependent assumptions. Substitution on terms, context equivalence, equivalence on both unconditional and dependent evidence in the form of reflexivity, symmetry, and transitivity, equivalence on lambda terms, equivalence on the beta eta radixes for box and diamond, and for the introduction rule. So these are this seems to be to show that the system is well behaving, though it is a splitted version of a standard system. Now, what is the real problem is here normalization, and this is basically what I will try to work on and solve in the next few weeks. So what is the problem here? The problem can be explained as follows. If you see this, this schema here, you will see that we start from on the right up corner from dependent evidence, a formula which contains a dependent evidence, and we transform it by eta equivalence to the corresponding implication by discharging. Now this can be done. On the other hand, the horizontal transformation is a beta equivalence, which brings the discharging of the assumption. On the lower equivalence, we have an equivalence on the box, a beta equivalence on the box operation that also gives the corresponding elimination rule. Now, this diagram commute because it means that all the assumptions have been discharged and one can transform all the possible equivalence rule. The point is, if the following, which is admitted by the system, is done, namely on the lower transformation, the transformation on the bottom is not given according to the box beta equivalence, but is given according to the diamond beta equivalence, then what happens is that one gets this operation, which is the operation of picking up an assumption which is not yet discharged, and this will not commute with the corresponding discharged assumption. So this shows that in the system there are two possible transformations that do not necessarily commute do not necessarily commute both. So we will have to find out a way to be sure that every time one gets a formula of this form, one is able to reduce this to a corresponding formula of the on the left lower corner of the first diagram. Now, for this, there is actually a solution, and this is a strategy of two normal forms, which has been given for dependent types. And the idea can be explained as follows. Basically, one takes care that there are two normal forms. One is called full normal form, the other is called internal normal form. And one takes care that every expression of an internal normal form actually is always an intermediate step to a full normal form. If this is done, then one can show that every formula that has this normal form will eventually lead to a formula of the FNF normal form. And the FNF formal form then is the one that takes care that reduction always occurs. So what do we basically have to do is to define eta expansion for as rewriting rules for the two normal forms, then show that every one of the two normal forms ends in a beta normal reduction, and to show that equivalence preserves beta reduction. So basically that once you get to the internal normal forms, you will always have a next step in the derivation that reduces to the full normal form. And if this is done, what one will be able to prove, supposedly, is that, well, full normal forms for terms are normal forms, that confluence is satisfied in the following way. So both rewriting rules for internal and full normal forms leads to a unique form, that every term reduced to a normal form, that reduction preserve beta normal forms, and then finally normalization of the rewriting rule will be given in terms of the eta equivalences. And if confluence is proven, then the following will result as a lemma. This is the idea of the strategy, namely one will get to the point where there is no infinite reduction, because not every expression will in the end lead to a normal form, which is the final normal form. So this is a bit of a sketch of what actually needs to be done in order to show that the system is well behaving, and that basically the extension of the standard system with the notion of dependent evidence is conservative with respect to the system that contains only simple evidences. So just my summary, the idea is to extend the intuitionistic version of the logic of proof with a functional fragment, then to translate this into a natural deduction calculus, which is able to take apart unconditional evidences and dependent evidence in the way I've explained, namely where independent evidence is an evidence that is derivable under valid assumptions only, and dependent evidence is an evidence that is derivable from true assumptions. This can be extended to extensional equivalence pretty much in the same way that extensional equivalence is proved in theories of dependent types, and the main task at this stage is to prove that the extensions by dependent evidence is conservative with the calculus of simple evidence in terms of strong normalization. And I think that's it.
So you're starting this using an intuitionistic logic of proofs, but is that really essential? I wonder if some of this could also be extended to the context of classical.
I've been wondering that too, okay, maybe I should say this, that the inspiration for this comes from the fact that I've been working mainly with constructive type theory and type theory, so I've always wondered why there wasn't a neat interface between the logic of proofs and intuitionistic type theory, given that they rely basically on the same assumptions. And I realized that one way to do this would be to extend the logic of proofs in the same way that dependent types are given. So I've started with this, and I've also wondered if that is just a property that can be preserved under the intuitionistic logic. But I'm not sure if, probably it can, but I'm not yet there.
Other questions? If not, let's thank again.
Thank you.